So in this video we're going to be looking at functions, but we're also going to start the grade 12 curriculum. But the functions, what we're going to do in this unit, I just want to do a quick review of functions before we start expanding our knowledge on it. So we remember from functions some of the key things that we need to remember. So the notation, first of all, f of x is equal to whatever the function is, like x plus 1. You have to also remember when we do have any sort of, like, say, function, we need to remember that every input only has one output. So for every x value, we should have one output y value. So another way of looking at that statement is the vertical line test to see if something is a function. At every time you draw a line down the vertical axis, you should have only one. Doesn't matter where you put this line, it should only go through it one time. What else can we look over? This is an example of a function, but you can also have an example where it is not a function. So it's something like this would not be a function, because you do the test, you have two spots here that would be defined as a function. Let's remember what absolute values are. If you remember, we had, say, the absolute value of -3 is equal to 3, and the absolute value of 3 is also equal to 3. So let's remember, we have to keep that in mind and remember the function for say y equals the absolute value of x. That is going to be, so y equals x is this, but the absolute value will not be negative, it will also be positive. That is our absolute function. We have to remember that. I don't know if we covered these things, but there are some definitions that we can go over. So something called the interval of increase. The interval of increase is basically the interval or intervals, it could be plural, of a function's domain where the y values are getting larger, so moving from left to right. And then we also have, let's just put decrease as well, and that's the exact opposite. I think we did do this. No, we didn't do it. So we can learn also about odd functions. Just brush up on odd functions. An odd function, you have to look at the degree of a function. So y equals x squared is an even function, because let's just put even / odd. This is even because 2 is an even number, and what happens is that y equals x squared will do this. It'll come from up and finish it up, or if you do negative, it'll be like this. It'll come from down and end it down. So it's an even function. An odd function will do something like this. It won't go in the same direction that it came from. So it came from the bottom but ended at top, or you can have So those are things you can look at. Another two things that we should keep in mind are something called a continuous function, and that is basically a function that has no breaks in it, has absolutely no. Well, this is gonna lead into the next a discontinuity could be like, a discontinuity is a break in the graph. So that point at which it breaks, that's where it's a discontinuity. For example, when a graph will do something like this. If it has this the y-axis as an asymptote, that'll be a discontinuity because it has points for every x value except 0 for x equals 0. So yeah, we do remember our domain and range. Domain is where we can define all of our x values, and range is where we can define all of our y values. So a lot of fun things to go over. If you need a refresher on how to map out graphs, there's tons of videos that I've already done graphing different types of, or sketching graphs of different types of functions. You can just go back there and like see what you want to relearn. What else can we do? We can go over inverse functions quickly. In which, if you remember, if you look at it on a graph, like if you had, say, a function like this, if you drew out an imaginary line like that as y equals x, you would just flip it upon that. So whatever this is, you just flip it like that, in which this would become like that. But if you wanted to do it algebraically, you just swap out the x and y and isolate for y again. So for example, if you took the volume of a sphere, which is volume equals 4 over 3 pi r cubed, if you wanted to find the inverse of this, you would just isolate r. Right now, v is a function of r. So if we swap it out to make it the opposite, we can do multiply this by 3. 3v equals 4 pi r cubed divided by pi r cubed is equal to 3v over 4 pi. And then we do cube root r equals almost done. So we think that is a good place to stop in terms of functions. It's basically just a review before we get into the actual, when we go into the next chapter, where we start learning about, we start interpreting functions as rates of change, where we have things such as meters per second, or meters per second, which is meters per second squared. This would be speed, this would be acceleration, all things that are used very heavily in the real world. So stay tuned for that. And I think I'll just stop this one here, and I shall see you in the next one. Okay, so in this video we're going to be looking at the rate of change. So the average rate of change, by definition, is, in relation to the change of a quantity given by a dependent variable. So for us, let's say it's y. So the delta in y over a corresponding change represented by another independent variable. So let's say x. So for us, mainly what we're going to do, in many cases, will be a change over time. But we can keep an open mind. So if f of x, if y is equal to f of x, then, and say x1 is smaller than x2, then we can say our rate of change, our delta y over our delta x, is f of x2 minus f of x1, which are y values, over x2 minus x1. And this is going to make more sense in a bit when we look at an example. I'll just leave that there. So let's look at an example with, say, bacteria. Say we have time. So our time in hours. Let's say we have 0, 2, 4, 6, 8, 10, and then we have 850, 11, 22, 14, 81, 19, 54, 25, 77, 3400. See, we're looking at this chart. And say we have bacteria here. Now we see at 0 hours we start off with 850, and then we have 1122, and then we have 1481, then 1954, 2577, and 3400. So say we want to look at the rate of change. And we want to see the difference in the rates of changes between each one of these intervals. So let's look at 0 to 2 hours first. So let's do the rate of change between those. How much bacteria did we have grow write that here. So 136. Let's put delta, just to see the rate of change. Now we can do the rest for the others. So say we have, oh wait, that's gonna get confusing. Let's do for these two. And then for these two, and for these two, and these two, and these two. So we found this one to be 136 difference. Now you see the time is growing at a steady rate by 2. So all I need to do is take the difference between this value and that value and divide it by 2. So this one will give me 179.5. 1954 minus 1481 should give me 473 over 2, 236.5. This one, 2577. Subtracting 1954, that should give me 8623, and then divide that by 2. I should get, what is it, 311.2, sorry, 0.5. 311.5, and then we have 25, no, sorry, well, 3400 minus 2577. When you subtract those two, you should have 823. You divide that by 2, you should get 411.5. And you can see the rate of change is growing. So not only is the bacteria growing over time, the rate at which it's growing is growing as well. So if you were to draw that out, well, here, and you had like, say this is 0, then you had like, well, let's draw these out. So 1000, 2000, 3000, you start here, and then you do like intervals of 0, 2, 4, 6, 8, 10. It would go somewhat like from here, that's 10. Let's do 2, 4, 6, 8. 6 is like somewhere in 1900s. 8 is like 25 something. It'd go like, so my point is, it's not like it's a straight line, it's actually a slight curve. And that is the rate of change, which is changing. And you can actually find the rate of change at any given point by finding a secant line. So what is a secant line? So say you have this curve. And you want to find out the rate of change here. All you have to do is plant a line that goes through that point. Or sorry, if you want to find the rate of change between, no, this is a tangent line that I just almost confused a lot of people there. So let's tackle one more example. So let's do an example of, say, the real world where you have say you're doing a car rental, and the car rental charges you $35 per day, plus an additional 15 cents per kilometer that you drive each day. So we can say that we're smart enough to write a function for this. So the cost of the distance, or the daily car, or the days, the cost of each days is going to be 0.15 times d being distance in kilometers plus 35 on any given day. So now we can look at the average rate of change here. So if you were to draw this out or sketch this, we could say that this is the distance. Say you start off at 0 and you can do 50, 100, 200, 300, so on. Oh, that's not even, should be 150 and 200. Then you do the cost, 10, 20, 30, 40, 50, 60, 70, 80, and so on. So we know that if we were to draw this out, we start at 35, and then we do 15 cents per kilometer. So the more she drives, it just keeps going. So we can tell this, or we can see right away that the rate of change is constant in this one, in this example, because our line is straight. And if you were to pick any 2 points here, say 0 to 100, let's say at 100 she's at 50. Let's just say that's true. And then you would have plugged it into the formula delta C over delta D. Delta being the change in the cost. Oh, this is the cost here. The cost, the charge at 100. So C at 100 minus C us using math to state the obvious. So yeah, rate of change, heavily used in physics and chemistry. So stay tuned in the foreseeable future when we cover physics. It's going to be fun to learn about all the different types of deltas and rates of change. So yeah, that is all for this video on rates of change, and I shall see you in the next one. Okay, so let's solve problems involving rates of change. So let's go with an example. Say we have a Ferris wheel. Let's pretend that looks like a Ferris wheel. And say that we have the elevation from the ground to any given point at where a certain person is. So let's say I am on this Ferris wheel and I'm here. And we're going to say that h of t is going to represent the height above ground in meters, where I am, and t is going to be time, and the function that's going to represent my height is going to be 5 cos 4 t minus 10 degrees plus 6. It's going to be a cos wave because I am going up and down. So we want to see at what time, at what exact time. Say we're going to take an educated guess and say at 55 seconds I will be closest to the ground at here, and we're going to try to prove that or check it or see if that's true. So what we're going to do is, instead of 55, we're going to look at 54 to 55, because basically when we look at the rate of change at these two, if we have a rate of change that is going very at a decline like this or an incline like that, you're going to have a proper number, like a number that's going to be really positive or really negative. But at the very bottom, you're going to have a line that is a rate of change that is very close to it's going to be like this. That line, the tangent line, is going to be 0. Or, yeah, 0. So, let's look at the delta here. So we have h at 55 minus h at 54 over 55 minus 54. So if we plug in 55 into this in a calculator, we should get 1. And if you punch in 54, you should get 1.0122. And you divide that by 1, you get negative 0.0122 meters per second. Because remember, our numerator is in meters, because h of t is the height in meters, and t is in seconds, so we are doing meters per second. And now we're going to do the exact same thing with h at 56 minus h at 54. And that that is going all divided by 56 minus 55. So let's just put a line here. That's going to be 1.0122 minus 1 over 1, which again is going to give us 0.0122. So, what do we know now? That based on this information at 56, you're going to have 1.0122 meters above the ground. So if you had like a like the bottom of the Ferris wheel, this is 1 meter above ground at 55 seconds. At 56, it'll go back up slightly more. So this is going to be 1 meter, and then this is going to be, at 56, it'll be 1.0122, and then at 54, it'll be right here, the same as 56. It'll be 1.0122, and there you go. So basically, the rate of change that we've seen from here to here is negative, and the rate of change from here to here is positive. But if we did a rate of change from here to here, you'd have 0. So it's not unwise to say that the lowest point will happen between 54 and 56. So 55 would make a great estimate and therefore would become the lowest point. So let's look at one more example with the rate of change. So let's say we have f of x equal to x squared plus 4x minus 21. And we want to see that, or prove that at x equals negative 2, that's where the minimum point happens. So we know that this is a parabola with a positive in the front, so it's going to be like this somehow, somewhere. I don't know exactly where, but it's going to be opening upwards. So let's find or prove that x equals negative 2 at some point. So the way we're going to do this, we're going to estimate going to basically say that h is going to represent a small amount of difference from the -2, and we're going to find the delta from there, the difference in that height. Remember, this is a generic way of finding a slope. This just means that a point at -2 that is just slightly off by a little bit, we're going to use that point and the difference from there to find a slope of a tangent line. So to find or to estimate the slope of the tangent line at x equals -2, well, this is why it's going to be somewhere here. Let me just correct that. Let's put this somewhere. I don't even know, there. At x equals -2, we're going to use 2 points and the difference quotient. So for 1 point, we're going to use this. Well, actually, we're going to use -2 comma -25. So let's put that there. So with that point, and then we're also going to use another point which is going to be generic. So that point that we're going to be going towards is going to be -2 plus h, the x coordinate, and then the y coordinate is going to be the f of that. I hope it's not super confusing. Once we plug it into our slope formula, it'll make sense. So when you plug these two numbers in, you're going to have something like this. Let me put that somewhere else. And now when we simplify this, well, this is all still over h. So when we simplify this, we're going to get we should get 4 minus 4h plus h squared minus 8 plus 4h plus 4 all over h. So the plus 4 and minus 8 will cancel out. The -4h plus 4h will cancel out, leaving us with h squared over h, which is just h. So if we were to use a very, 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 very small value here, so all we've done so far is prove that we can use h as a small increment here. So we know that the slope at where to 0. The slope will be 0, so we can say that h is going to be so small. It'll actually become the slope at which we're changing it at, and also so when we look at these two differences, one here and one here, when we do the delta of the two, so say we do the delta of these two rates, so we can have 0.01 plus negative 0.01 over 2. And we're going to have, basically this is going to cancel out and give us 0. By that logic, using 0.01, we can prove this, that at f at negative 2, you have negative 25, correct? But if I add 0.01, I'll get, well, that's not 0.01, that's 0.1. I should get negative 24.99 if I plug it into this formula. And if I go over f at negative 2.1, I'll also get negative 24.99. And there you have the difference, that h value that we were looking for, this one and that one, they're off by 0.01. Which was our h value that we used. So we can say that because the tangent line that we introduced, since that is equal to 0 when x is equal to negative 2, and also since the values just around f at negative 2 are greater than the value at x equals negative 2, our minimum occurs right here at x equals x equals negative 2. So I hope I confused you as much as I confused myself. But yeah, that's all for the video on solving some problems that have rates of change in them. And I shall see you in the next one. Okay, so in this video we're going to be looking at polynomials. So let's start with this. F of x is equal to negative 3x to the power of 5 plus 4x cubed minus 8x squared plus 7x minus 5. Say that is my function of x, and basically what I want to do is just look at this, and just by looking at this I want to come up with a rough sketch of what this function might look like. So there are a couple of things to note here. One thing that we're going to do just to find the behavior of this is to see the behavior of the function when we send the x value towards infinity. And well, first we'll start with negative infinity, and then we'll go on to the positive infinity. So in the x value is going into the negative side. If I was to plug in a very big negative number into this, the biggest factor influencing the output here is this right here, this first term. Since this first term is to the power of 5, it's going to have the most significant impact on the behavior of this polynomial. So if I put a gigantic negative number, it's going to be a positive number here. So I can say that as x, the value of this function, whatever's going into this way, into the negative area, I know that I'm going to get a y going to upwards of a positive number, so this is y. Y will go to positive infinity. And similarly, if I do the same for a positive value, I'm going to get a negative value. So as x goes all the way to the positive infinity, a big number will only get me a negative output based on this first term here. So I'll get a negative infinity for y's behavior. So far I have the behavior of the positive and negative values of the function. Next we're going to look at the zeros of the function. So, based on what we have so far, with the value going like that and ending like that, this could be looking like that, something like that, or it could even look like, something like that. So that's what we know so far. But then again, we can also look at other factors here. Let's just draw this out again. So when we look at the zeros of this, so if we were to factor this completely, we have 1, 2, 3, 4 of these. So yeah, based on what, just by looking at this, we could say that this f of x function can have 0. Let me just 0, 2, or 4 turning points. So it could not turn at all, or it could turn once and then twice, or it could do this 1, 2, 3, 4. Sorry, 1, 2, 3, 4. So that's 1, 2, 3, and 4. It can go up to 4 times, but that's it. It cannot go more than that because of its degree. So let's look at the degree of the polynomial being 5. So that's the highest degree right there. The degree of the function is 5 because of its highest term exponent. So because this is 5, we can say f of x will have at least 1, 0, but also max 5 characteristics. So this right here, and then this part, and this part. These are characteristics we can take away just by looking at the polynomial, that it could actually have 1 0, so I can do this 1 0, or it can do 2 zeros. Sorry. Yeah, it can like do 1. Like that, 2 zeros, or even 1, 2, 3 zeros. You get the point. But basically, I'm saying it can have zeros. So that is a few things. It's going, or some characteristics to look at when trying to understand the behavior of a polynomial. And behavior, this is what we did here. And behavior, to see what happens when x goes to negative infinity and the positive infinity. And then we also want to look at the leading coefficient of this, the negative that we have here. That plays an impact on the behavior there. And then we also want to know that if this degree here, is it positive or negative? Because a negative, sorry, what am I saying? Even or odd. Even means it will do whatever it does, but then end up in the same direction it came from. Odd will do, so it can do that, or it can go like that. But odd, in our case we have odd, it will always start on one side and then end the other side. Same like for me. So if that was a positive coefficient, it would have done this. But since we have negative, it's doing this. And then like we looked at the number of turning points. So if the degree is n, it will have n minus 1 turning points. So our case is 5, so it'll have 4 turning points. What else? Number of zeros. It will have if n is degree, n minus 1 turning points, up to n zeros. We can have up to n zeros. So these are the main takeaways from I guess this that example. I just wanted to introduce that example. Let's try doing this let's continue on polynomials. I don't want to finish up so quickly there. So let's say we want to have a cubic function. And we want these 3 zeros. We want the zeros to be at -2, 3, and 2 over 5. So we want these zeros, and we want to write a cubic function, and we want the y-intercept to be 6. So let's write this out. minus 2 equals 0. So I can put that in here. 5x minus 2. Can't say I didn't explain. So that is our formula, and we want to find our a value. And lucky for us, we have a y-intercept, which is a point. So that will give us x comma y 0 comma 6. So our f of x value of 6 is going to be a, and then our 0 plus 2, 0 minus 3, 5 times 0 minus 2. So we have a times 2 times negative 3, 5 times 0 is 0, so negative 2. So we have 6 equals 12a, and that leaves us with a equals 1 over 2. So now we know what a is, we can just put that back here. And see how easy that was. We found a cubic function with the 3 zeros and its y-intercept. So, very straightforward stuff. Well, that's all for this video, and I shall see you in the next one.